still a number of people milling around in the hallways, but I'm Richard Voiles from Purdue University, and it is my great honor and privilege today to introduce our keynote speaker. He's a man that really needs no introduction, which makes my job easier, but also I enjoy this job because Satoshi has been a longtime friend of mine from SSRR, and that is what makes, of course, Satoshi such a wonderful speaker for us. He is the president-elect of RAS, so I'm sure many, if not most of you know him already. He has a distinguished career, and I'm not going to go over the details since we have a minimal amount of time, but he comes to us from Tohoku University as professor. He has formed the International Research Rescue Systems Institute and has been serving on the graduate faculty, again, at Tohoku in the Information Sciences for a long time. He's been involved in government and academe and, again, outreach for safety, security, and rescue research. Most recently, organized an effort with the UN, and that is part of what he is going to speak to us about. And so without further ado, I would like to bring on the stage our RAS president-elect, Dr. Satoshi Tadokoro.
Thank you very much, Richard, for kind introduction. Today, I'd like to talk about toward social implementation of disaster robotics. So this is on content. And yes, what is the role and needs of disaster robotics? The robotics is used when the human cannot do at present. So that means, for example, the place where inaccessible of human, or when there's a risk, or when the robots are more efficient than human. So that is the reason why robots are used. So the purpose of the robotics is for information gathering and recovery works. And this is a disaster cycle. After the breakout of the disaster, the response phase starts. It continues for a few days or weeks, and then recovery phase starts. It continues months or years. But before that, the preparedness phase is really important. It continues more than 10 years. So sometimes we are focusing only on the response phase, but for the disaster prevention or disaster mitigation, preparedness and recovery are also very important issue. So we should consider how robotics can contribute to the preparedness and recovery in addition to the disaster response. So the Fukushima Daiichi incident was really serious. And after the 3.11s, several types of robots are being used. And they are really effective for the decommissioning and also after the response. And our robot Queens was really successful. It could survey the second floor of the nuclear power plant. And yes, we could gather several informations. And it contributed significantly for the planning of the decommissioning and shutdown of the reactors. However, this creature was not intended for the nuclear power plant accident. The main purpose of the development of this creature was to respond to the CBRN type disaster which happens in the underground cities. So in underground cities, the firefighters suffered from the chemical agent or something. So in this case, the robot, the substitute human, and it enters in the dangerous situations and gather information. That was the purpose why we developed that. And the starting point of our disaster response robotics research was the earthquake disaster. So we were really interested in the rubble pile and rough situations. So the mobility was really one of the top issues of our research and development. So this is a previous version of Queens called KENAF, and it was tested in the several situations like this, or this was E-Defense, the world's largest shaking stage of which tests the structures. So this is a real 3-story houses, and using this good opportunity of testing the robots, we collaborate with the architects and also the firefighters. We tested this KNAF in these situations. And before the 3.11th, that was March 9th, 2011, two days before, we tested the Queens at Disaster City, and we are really happy that the Queens could be used in this really hard rubble piles. This is 40 meter by 40 meter size, big, huge rubble of the wooden structures. And these Queens could traverse from one side to another side successfully. We are really happy at that time, but after that, something happened in Japan, and we returned to Japan immediately. And this technology is transferred to some companies. And for example, this is an example. Japan government has some project of the fire department management agency firefighting robot. And in collaboration with the Mitsubishi Heavy Industry, we are developing robotic systems for extinguish and prevention of propagation of petrochemical plant fire. So the technology is the autonomously placing a water gun and hoses near burning tasks. That is a result of the extension of the disaster response robot research. And also, we developed active scope camera. That is a thin type, snake type robot, which the purpose of development is the search in rubble pile. And this was applied to the real disaster which happened in Jacksonville, Florida in 2008. And the construction site collapsed in this way. And for the forensic investigation, this active scope camera was used. Several robotic systems or some the video scope was tried, but it was not a success. However, this snake-type robot can enter deep in the rubble pile 8-9 meters, and it could capture the image inside. So it was really successful of missions in collaboration with the CRACER, which is organized by the Professor Robin Murphy in Texas A&M. And this is a second deployment of the active scope camera, and this was a colonic historic archive collapse. And it collapsed, and we were called out for the search and rescue missions. We stayed 3 nights near this colonic historic archive. However, our active scope camera was not used, unfortunately. The firefighter managers decided the risk is too high to use this active scope camera. And after that, it was transferred to the Shimizu Construction, which is a major construction company in Japan. And their mission was to make surveillance of information gathering in the nuclear building #1 in the Fukushima Daiichi. It has a roof, and they make a hole on the roof, and they wanted to make a map and a situation map in the rubble pile. So they collaborated with us to apply this active scope camera technology. So they developed a crane system, and on the crane system, this new type of active scope camera was installed, and it is planned to be used in the actual plant. This is the experimental result of the active scope camera, and it successfully entered in these situations. It simulated the inside of the nuclear reactor building, and it could survey and made a map of the inside of in this rubble pile. And also, this technology was transferred to the gas companies who wanted to inspect the thin pipe, which connects the main big pipe with houses. So the diameter is up to 1 inch, so it is really thin. However, this active scope camera was revealed that it is really effective for this purpose. So we could capture image in the 1 inch pipe with 6 bends successfully. That was maybe really, according to them, it is much beyond the existing technologies. And also, this is similar applications about the 3D shape measurement of underground sewers. So Japan has so many aged sewers. It is more than 30 years old, and it is a really big social problems. So we applied our mapping technologies to these issues, and it is really successful for producing some product for the underground sewer measurement. And this is a collaboration with Vijay Kumar in University of Pennsylvania. That is UGV, UAV collaborations. The lower part is UGV, our UGV Queens, and upper part is a Pelican, which is developed by Professor Kumar's group. However, the UAV can fly only a really short time, 10 minutes, 20 minutes. However, therefore, it is impossible for this UAV to make a map in the big buildings. However, the UGV can survive for a long time. On the other hand, UGV has a problem that it cannot enter narrow space. So the collaboration of the two robots were really effective, and as a result of this experiment, it could make the map of the whole building from 4th floor to 8th floor. It was actually damaged building in Tohoku University electric department building. And it was really successful. But it was not the actual mission, it was experiments there. And this technology was transferred to the really planned missions for Fukushima Daiichi. And the TEPCO, Tokyo Electric Power Company, wanted to make a map in the buildings. And there remains some places where the robots nor human can enter. So using the UAV and the UGV, they wanted to make the map. And this is a picture of the testing, and we could successfully made a map, but the reliability was not sufficient, and so we're waiting for the actual missions. And this is another application of UAVs. 2 years ago, a new student came to my laboratory, and he proposed a development of the ball-type UAVs. That is, he was motivated by the invention by Japan Self-Defense Force, and they developed a ball-type UAV. So his proposal was to apply a gimbal structure for the UAV. Okay, so we made a discussion, and he started the development. In the summer, he was really successful to develop this creature. However, after that, I attended the IEEE.RAS, and I found really similar inventions, presentation by EPFL people, gimbal. So the difference was gimbal has only the one rotor, but ours has 4 rotors. Apparently, the people in the EPFL is the first, and we are the second. But anyway, we are really interested in applying this creature to the bridge inspection. So this is actual the bridge, which is this test was facilitated by the Ministry of Land and Infrastructures of our Japan government. And this is another testing. And under the really high wind speed of 99 meters per second, our gimbal type UAV could fly successfully and made a surveillance of map and made a map of the damaged or crack of the bridges. So it was a really successful model, and maybe in the future, this or some similar robots would be used in the actual missions. And this is another one, rescue robodoc. The objective is, the research objective is integration of the digital system with rescue dog. The rescue dog is a dog, so that is for users. It is really difficult why it is barking and where it is. By using GPS, IMU, and camera, and so on, we can monitor the behavior of this dog, rescue dog. So this is one of the results. It could measure the motion of the dog and capture the dog behavior, and the operators could know why dog is barking. And this picture shows what the dog found. So those are some introduction of the research of our group. And apparently, I think the science and technology are becoming ready for the real disaster missions. And however, according to Robin Murphy, who is a top person in the disaster robotics, there is still gap between the robotics and social implementation. That is a serious problem. So we have to solve those problems in order for the robotics to have enough power for the disaster missions. This is really conventional, well-known technology readiness level definitions from level 9 of practical level to the level 1 of scientific discovery. Usually researchers are focusing on the low level from universities, and the industries focusing on the higher level. If there is enough market, industry can do so many things. So from level 1 to level 9, continuously make transitions, and all that science and technology can be used. However, in the disaster domain, it is somewhat difficult. And from the viewpoint of the social people, so the general public, their expectation is a little bit different from the achievement of the science and technology. We are really focusing on the writing good papers, but it is independent from the how practical they are. So we should consider that. So I think there are several necessary conditions in order for the disaster robotics to be used actually. The first is, of course, the science and technology. The technology should be ready for practical use. That is a matter of course. However, in addition to that, we should consider the hidden user needs or hidden conditions are required. For example, if we use a robot in some petrochemical situations, the anti-explosion is really important. But the usual university researchers would not like to consider that. So that kind of gap exists. And also, robotic solutions should be economically effective. That means the robots should be enough cheap. So that is really important for actually used. And also, robotic solutions should be convenient for users, easy to use, and that is also very important. In addition to that, there are several necessary conditions of users. So users have well-recognized ability and limitation of robotics that is necessary, and robotics should be should have been deployed. And also, it should be continuously used, tested, exercised by the users. That is very important. And for that purpose, law, regulation, and social systems should be appropriate for this purpose. And also, the user communities is really important. So is this academic work? No, totally not. But in this domain, we should consider carefully that if we want our robotics is used. And third part is a necessary condition of industries. Robotics business and investment should be successful, and system of distribution, maintenance, user education, and so on should be set up, and human resource should be enough, and international market and standards should be ready. Those are really important things. However, I am in academia, and many people are not working for setting up these conditions. So in order to lower the social barriers, we have to do something. So the IEEE Robotics and Automation Society organized public forum in this conference. This was the United Nations World Conference on Disaster Risk Reduction, which was held in this March in Sendai. So at that place, we announced a voluntary commitment at the working session in main conference. So this is a structure of the United Nations, and there are several offices. And among these offices, two are really related to the disasters. One is UNISDR, United Nations International Strategy for Disaster Productions, which focusing on the preparedness. And OCHA, Office for the Coordination of Humanitarian Affairs, which focus on the emergency response. So this World Conference is a main conference of the UNISDR. And 10 years ago, this conference was held in Kobe. And they adopted a Hyogo Framework for Action, HFA, which defines the necessary actions in 2005 to 2015 for 10 years. And it had a major impact on national policies of disaster prevention for 10 years. So I wanted to, however, in this HFA, it didn't include any keyword of robotics. So I wanted to have this keyword robotics in the next framework, which is announced in the Sendai. So they adopted the Sendai framework for disaster risk reduction, which is planned for the 15 years. But our action, the RAS action was too late, and it was not impossible to include the robotics, but it was really happy that I was really happy because the disaster managers and the United Nations people recognize how robotics is effective for the disaster prevention in the future. That was a really nice achievement. So they are the 7 global targets, and it includes the last part, the multi-hazard early warning system and disaster risk information and assessment. This is very important. That is included. But this apparently includes robotics. The question from the United Nations was what robotics can do. So we made a statement that an international committee shall be established as a way to accelerate the implementation of robotics and ICT for national disaster management plans and national regulations, synchronized with rapid technology revolutions. This national disaster management plan includes apparently, for example, the budget raising in the government. So IEEE has a SITE. SITE is a IEEE Special Interest Group of Humanitarian Technology. It was established after the 3.11 incidents. So they are making several things, including the disasters. And according to the call from IEEE, Robotics and Automation Society established RAS Special Interest Group of Humanitarian Technology, RAS SITE. So the mission is as this. So what is the international committee in this declarement in the United Nations? So I plan to establish a subcommittee in RAS site for that UN voluntary commitment. So what is the mission of the International Committee? I don't know exactly what is the final missions. However, at least it includes the kickoff of action and collaboration of the stakeholders for the social implementation disaster robotics, and it should provide a forum of discussion, and it should match the social needs and technology sees, barring the gap. That is really important actions from RAS, not only about the technology, but also the industry and social things. We'd like to contribute for reducing disaster risks. It is really important mission for us. Thank you very much.
All right. Thank you, Satoshi. We have time for a couple quick questions. If anyone has any questions. In terms of the reception, I have a question. In terms of the reception of the UN community to this proposal, obviously it was successful. Can you give us more insight on was the expectation, I guess, of robotics in this arena?
Yes, robotics is really different from the passive distributed sensors. Robotics can actively gather information for disaster management. That is their major expectation for response. However, for the preparedness, robotics is also really effective. It can reduce the cost of inspection or some maintenance of infrastructure of architectures. So it can significantly contribute to the safety.
Okay, thank you. Our time is just about up, and so I'm going to ask you once again to thank our speaker, Professor Tadokoro.
Thank you very much.